So hello everyone, my name is Veljko and I'll be there as a tech support during the tutorial. I want to introduce you to our tutor, Darja Cvetkovic. She's a research assistant at the Institute of Physics in Belgrade, and she will be holding reimagining data frames, an introduction to graphs and GNNs with PyTorch geometric tutorial. So everybody enjoy.
Hi, thank you, Eiko, for this introduction. Hello, everyone. Thank you for coming and tuning in for this tutorial. I think the organizer sent you a link to my drive with the data and this Google Colab that we'll be using, but I can, Veljko already shared. Thank you. So we can start. You can use your preferred editor like VS Code or something, but I'll be using Colab for this since it's more convenient. But if you use your own editor, you will need like this libraries installed. So Pandas, NetworkX, NumPy, Matplotlib, PyTorch, Torch Geometric, and Sklearn. Yeah, you can connect to a GPU runtime if you want. I don't think it's very necessary since this tutorial isn't going to be focused on training the models, but rather forming your data sets. So yeah, I ran this prior to tuning in, so everything is installed and ready. And first, I would like to start with a bit of motivation. So, what are graphs? If you already don't know, graphs are also called networks or complex networks, and they're structures consisting of nodes and edges or links between them. So, I've used NetworkX to draw a simple visualization of some graphs. So, like you can already see, these are the yellow circles are the nodes, and the edges are these lines connecting them. This makes graphs very convenient for representing a lot of different systems, like social systems, biological systems, transportational, recommendation, transactional, basically anything, any system, any data set, any problem that you can conceptualize and define in terms of like its constituents, and that would be the nodes, and connections or interactions, relationships, that would be the edges. Anything you can define in that terms can be depicted using a graph. This is especially important when the structure and the relationships, interdependence of the data points of the system or the data plays some crucial role. In the problem you're studying. I see one question for an anonymous attendee. You can, I think Veljko sent a link to Google Colab, so Veljko, maybe you can send it again.
We are having a little problem. We are working on fixing it. It will be in 2 minutes.
Okay, good. So yeah, just wait for the link. Everything is in there. I won't be typing anything new. And if I do, it will be synchronized, should be synchronized in the notebook. Okay, so yeah, this is just, like I said, some examples for graphs. You can use them as social networks. You can use them as like to represent molecules, where nodes would be the atoms and the edges would be chemical bonds between them. You can use them. I think this is an example for some transactional data when you can do some fraud detection. You can also use them for recommendation systems. This comes very naturally when you think about it, and so on. Like I said, you use your imagination, and you can, I'm sure you can think of many more examples. Also, networks or graphs can be as simple as complicated as you like. You can add, for example, multiple types of nodes. You will have that would make a heterogeneous graph. I will put an example later. You can have different types of edges. You can have directions between the edges. You can have weights in the edges. Basically, you can make your graph as complicated or as simple as you'd like, depending on your problem. Sometimes one solution will work better, sometimes the other. And as far as the technical details going, in Python, you have NetworkX library for network analysis and dealing with graphs, and you also have iGraph. iGraph is also available in R. I'm sure of that. NetworkX probably, but I'm not sure. But iGraph, you can use iGraph in R. I am more comfortable with using NetworkX, but iGraph also has a really good documentation, and it's more adequate if you have large networks, since it has a backend in C, so it's fast. Okay, so where do graph neural networks come in? Well, if you don't already know, just and for just a bit of extra motivation, graphs are really tricky to work with sometimes, and that comes also with machine learning, because they are, mathematically speaking, geometrically speaking, they're non-Euclidean, which makes the mathematical operations that you need to define for machine learning a bit of quirkier and trickier to define. And also now your data is not independent like you would have in like regular tabular data sets. Now the nodes are connected, and the structure of the network can be really is of crucial value, and you can just feed in your model node by node. And that's where graph neural networks come in. Basically, the main idea of graph neural networks is to somehow collect the information, which would be the features from the node's neighbors, combine them with their state, and update that state. So you get some node embeddings. For example, here for node 1, we would like to collect the information from its neighbors node 2, 3, and 4, combine them all together, and we would get some different representations depending on the information from the local neighborhood. And when we talk about graph neural networks, when we talk about the depth of the model, it represents how deep you would like your neighbor aggregation to go. So one layer would mean one neighborhood hop, when you would basically collect and aggregate messages from the first neighborhood. The second, two layers, you would collect the information from neighbors of neighbors. So for node 1, you would also collect the information from node 5, because it's the nearest neighbor of the node 4, and so on. Okay, I've seen, I think the link is up now, but yeah, so I can continue. Of course, if you have any questions, feel free to ask me during the tutorial or after. So yeah, basically, I won't go into details about GNNs. You can, like, different models differ between the functions that they're using to aggregate and update these embeddings. So you can, there's a lot of variety there you can use, but the principle is always the same. Typical tasks that you can do on graphs. So you can do some node classification or regression. For example, you want to predict the property of a node or nodes. You want to predict, maybe you can do edge prediction when you would like to predict some edge properties, or whether an edge exists or not. We would want to do that for a recommendation system or something like that. Also, you can do a graph classification or graph regression, where you make predictions for the whole graph. The easiest way for me to give an example for this is if you have some molecular data and you have a bunch of molecules and you want to predict some physical or chemical property between them, you would like to calculate the predictions on the graph as a whole. And I would like also to add a couple of disclaimers and things to be aware of working with GNNs. So you firstly, you have to think about you have like two options when it comes to actual learning. You have the transductive setting and the inductive setting. Again, I won't go into detail, but just I sometimes other tutorials and when people introduce graph neural networks, they don't usually mention this, but you have a transductive setting and inductive setting. In transductive setting, you it isn't the best if you want to predict on new nodes. You will use transductive setting when full graph information is available, when the structure is fixed, and so on. Basically, it's a bit of I won't say it's worse, but it has its own purpose. And inductive learning you would use if you have any kind of changes in the graph in time, or if you want to predict on unseen data, or even if you have like a very large graph that it's unable to fit like into a memory at once. Also, different tasks like node classification, edge prediction, and graph classification all have their slight little differences in approaches and quirks. So you may need to put some little extra effort to understand what's going on if you're new to graph machine learning. It's nothing hard, but I'm just saying it has little specifics that you need to figure out before you do your task. Also, this is just the basics, the basic tasks, but like even more sophisticated tasks can be figured, can be seen as some variation of these ones. And finally, some key ideas why we're all here today is what to keep in mind when converting tabular datasets to graphs. So to convert the tabular dataset to a graph, you will need to define the nodes, which would be unique entities, like, for example, people, products, atoms, anything like that in your dataset. Node features or node feature matrix, like similar to general machine learning, you need some features to, I mean, most of the time you need some features to learn on. This would be some basically variables or properties that you can use to describe the entities, the nodes. You will also need to define the edges. Edges are, like I said, represent relationships. You can think of them as like verbs or actions that you can define your problem with. So, for example, did this user buy a product? So you would link them if the product and the user, if they bought a problem. Or is an atom 1 connected to an atom 2? You would link them if they're connected with a chemical bond. Also, if like are these movies in the same genre? So you would connect all the movies that are of the same type, and so on. Also, you can define edge features, which also, like node features, are just some additional properties of these relationships that you would like to capture. So, for example, how high is the review of the product, the number of clicks of an item, and so on. And yeah, as you can see, there are many ways of doing this, and there is not one clear way. You would need to use your like imagination or some inspiration from other works, but you will need to be aware that graphs can be powerful tools, but sometimes maybe they're not the best solution. And that's not always clear. And like in general in machine learning and in science, and you would and in life you would need to test some tests and see what best fits your problem. But keep in mind that they can be very, very powerful. Okay, so technically this is just how the data will look like. For the nodes, it's basically we'll have a list of nodes represented by unique integers starting from 0. We will have for node feature matrix, we will have like a tensor that is that has the feature vectors in it describing so node 0, node 1. We will have the edges. And in NetworkX, the usual representation is like a list of tuples, where each tuple represents the nodes that are connected. So 0 and 1, 0 and 3, 1 and 4, and so on. You also have the PyTorch geometric way, which is what we need to do machine learning and to represent our graphs in PyTorch. This is called the edge index, and it's also two-dimensional tensor where one of the components are the source nodes, and the other component is the target node. So, like here, node 0 connects to node 1, node 0 connects to node 3, node 1 connects to node 4, and so on. Okay, so finally, imports. I already imported this, so you will need pandas, NetworkX, NumPy, and Torch, basically. And so we can start. First example is homogeneous graphs. Homogeneous graphs are graphs with a single node type. So it's a simple problem. And we will use this Spotify songs dataset that I found on Kaggle, and we will try to predict the track popularity, which would be some node regression tasks. So let's take a look. Okay, I've imported the data, and as you can see, the data set is, I think, quite larger than I'm used to working, but it has over 300, I don't know how to, 300,000 nodes, the tracks, where we have tracks as, we have track names, track IDs, the artist, popularity of the track, album. We also have some, the playlist which the track belongs to, the genre of the playlist. We have the key of the song, loudness, mode, and a lot of different numerical features that describe the song. And for the purpose of this tutorial, I will just, to keep the execution faster, I will just use a sample of the data set. So we have now 3,000 rows, and we have like 23 columns, which I cannot see in this preview, but let's just print them out. So let's see. Okay, we have a bunch of features. Like I said, track information, playlist information, and also like features of the tracks, numerical features. All of these, I think, in the Kaggle dataset, all of these are described, but it's not important for this tutorial that much. Okay, so first thing, we need to extract and map the nodes. Like I said, the nodes will be tracks, and we want them to have unique integers starting from 0. This is important because edge index, or edges in like the PyTorch formulation, will always be referring to the index in the node feature matrix. So we will, like I build a dictionary to map the unique tracks, because some tracks occur more than once, so we only need we don't need duplicate nodes. We define a dictionary that maps the IDs of the tracks to unique integers, and we remap the data set to use this notation instead. Okay, so now you can see we have we've done what we wanted, and yeah, here I think, yeah, we had this kind of coded IDs. Okay, so first part, the easiest part is done. Okay, like I said, some tracks occur more than once, and it's okay in this case because the features will stay the same. The tracks always have the same features. Like here we see that this Bruno Mars track, it appears in different playlists. That is the difference. That is why it occurs more than once. We see that it's in the different genre of the playlist as well, but the key, the loudness, the mode, all of that numerical information, considering specifically the track, stays the same. So with this in mind, let's see how many genres and subgenres and playlists we have. We have 435 playlists, 6 genres, and 24 different subgenres. Now the node feature matrix. Again, this will depend on your problem, and you will need to experiment which thing works best for you. But here I will use all of this numerical information, almost all of it available, to describe the nodes. So first off, we will sort the data set by its IDs. And I made a list of the features we would like to use. And then we would just select them in pandas. Again, so you see we have like some data frame for the node features, but we need to convert them to a tensor. This is done easily with NumPy and PyTorch. So we just convert this information to a tensor. Okay. Also, we will need to accept node labels or the features that we want to predict. The feature that we want to predict. In our case, this is track popularity. Again, we just select only the tracks, the unique tracks. We don't select duplicates, and select track popularity. Extract that to a tensor because that's what needs to be done in order to do some math on it in PyTorch. And now extracting the edges. So in general, this is the trickiest part when converting to a tabular dataset to a graph one. The trickiest in a sense that it will depend on your problem, and sometimes the solution might not be so obvious. And again, you can do many different things. There's no one rule of how you do it. You just need to, at least at the beginning, do something that would make sense for your data. So think about, okay, what is the most logical or apparent way to connect my unique entities or nodes. In this tutorial, I will keep it simple, and I will just, for this data set, I will use just regular edges, nothing fancy, no directions, no weights, no nothing. And the edges will have features, and I will connect the songs or the nodes if they are in the same playlist, same genre, and same subgenre of the playlist. So in this way, we can extract as much relational information as possible. We could keep just the genre, the subgenre, or the playlist, but I thought, why not use everything available, which is probably an overkill or too much. But again, this is just a toy example. We will need this ether tools module to make combinations. You will see later why of the edges. But yeah, firstly, like I said, PyTorch Geometrics expect the edges in like this form. But to remove, you will see the duplicates, because if we connect the nodes, if they're in the same playlist, same genre, and same subgenre, we can have some edges, some connections repeating multiple times. And I can leave that, but since I don't have any features, it would only like make the data more bulky, and no useful information would be added in that way. So I will remove these duplicates, and it's easier for me to do that if I use the NetworkX notation. So I first I make the list of tuples that will represent connections. Okay, so this is the function I wrote, so we don't do this in 3 separate loops for each of the edge types. And yeah, it basically simply just goes over the data frame and finds for each node the songs that are in the same criteria, genre, playlist, or something, and makes the or the combinations for all of these, makes the edges. And then I do that like for each playlist, genre, subgenre, and make a huge list with everything put together. We will do that now. Okay. Just so it's clear, if I'm confusing you, this is how it looks like. We have like over 1 million of edges, I think, and they look like this. So song 0 and song 130 are connected by an edge, and so on. Now I will remove the duplicates. Like I said, this is a simple function to do that. And again, we have like nothing changed. We just removed the things that have appeared more than twice. And that should reduce, yeah, it reduced to over 800,000 edges, which is still a lot, but better than 1 million. Okay, so in NetworkX, you can also visualize your graphs, and it also it makes possible a lot of different visualizations, or all of which almost, I mean, not all of them, but a lot of them are available in the documentation and some galleries that they have. I just did the simple, I won't run this because it can take a while, but you will get the same if you want to run this in your code. Basically, I just wanted to show you an example how this graph works. I used a sample of the data, plotted the edges. So we have, like, these are our tracks, the blue dots, and they're somehow connected. You can, what I wanted to say is you can do this in NetworkX in many ways. You can adjust the size of the nodes to be like, if you have some feature, you want to discern, node is bigger if the feature is bigger, different colors for different classes. Also, you can do that with edges. So you can get way more creative than I did here. But yeah, just it's fairly simple and intuitive to use. Now we need to convert the edges to PyTorch representation. This is simple. We just use the zip function and stack this like to separate the source nodes and the target nodes, and we put them together in a tensor that is needed for Torch to work with. So yeah, like you can see, nothing changed much. We just had different form. Okay, now building the data set, quite easy in PyTorch Geometric. You just initialize this data, an object, an instance of this data object. You put your X, which is your node feature matrix. You put your edge information, edge index, and you put your labels, and that is all. Now, the second part is defining your graph neural network model and training. Like I said, there are a lot of models out there. There are different ways to build them. If you worked with PyTorch prior to this, you will see that it's fairly similar to how it works. You just need to understand how these layers in graph sense are defined. Here I will just use a simple GCN model, which basically aggregates the information as simple as just average of the features from the neighbors. I've defined 2 layers, so the GCN convolution, I think CNV is the layer that is used for GCN model. You just need to get a number of features and a number of like hidden channels, a number of neurons you want. Added a simple layer for more at the end for more expressivity. Define the forward function, which is how the message passing is done in this case. So first we go through the first layer, collect the basically the information from neighbors. We do some activation. Also, we do a dropout. You can do it. You like, again, this is fairly modular. You can do whatever you prefer or what works best. Again, then we do a second pass. So we collect the information from the tracks neighbors. So the second neighborhood of the tracks. And yes, we at the end we return some value. Okay, so that's it. Again, if you have any questions, ask me. But again, the training is not the purpose of this tutorial, so I'm just letting you get a picture of how it works. Okay, we can also train the GET model. It is a bit more sophisticated, and now it not only this model also includes it weighs information from neighbors. So not every neighbor will be as valuable to a node as the others. So this is what this layer allows us to do. So adds a bit of more complexity. Again, this is the convolutional layer you would not use for this. There's also some additional information because you can see this is mathematically more complex than the simple convolution model. Again, we can define that. We can do train test split with this random node split function. This will basically create train, validation, and test masks, which will have like true or false values. They will mask the nodes in the training. So in the test set, the nodes will still be here, but no predictions will be done on them, but they will be used maybe for message passing or so on. If you are interested in graph neural networks, you will see why this is done. Again, so yeah, you don't remove the nodes. The splitting isn't removing the nodes from the data. It's just masking them. So some of them are used in the predictions and some of them are not. And the training, you would basically define the model as you would in PyTorch, get them to a device if you're using CUDA or GPU. You will also move the data, define the optimizer, define the criterion for your task, define, if you like to define functions, you define train functions. Similar to PyTorch, you need to do this clear gradients, derive gradients, and update parameters. The model takes in the node feature matrix and the edge index. And again, similar, that is all. You would train them. This is looks, I think it executes fairly quickly for our data, but okay, I didn't run this. Okay, so this is, I mean, the results are awful, but I reduced a lot of data and I didn't like do like any sophisticated reductions, feature selection, and anything. And I also train for only 500 epochs. So, but we can see the loss is decreasing like we expected. If you would like to play around with it, you can do a lot of stuff and maybe play around with the models, play around with your data and see what works best. And then this is for the first example. I will like to show you how you would do this for a more sophisticated so more sophisticated case when you would have different node types. Are there any questions so far? Can we move on to the next section? Okay, let me just see. The widget is not okay. I see no questions, so I can Move on. Okay, so heterogeneous graphs are graphs that have more node types, or maybe even more edge types, but in this case, more node types. This would be the case, for example, in recommender systems. You would need, so first type of node would be the users, and the second node type would be products, for example. And here I will walk through an example for a book recommendation database. I have also found it on Kaggle, but I have reduced it prior to for this tutorial because it's quite large. I didn't want to encumber the notebook. Again, you can play around with the whole data set if you'd like. And also there's a very good and comprehensive example on link prediction for the movie lens dataset on the PyTorch Geometric's official site, and here's the notebook. So anyway, yeah, this data consists of three data frames. The first is the books data frame, the second is the users, and the third is the ratings. Okay, let's see how the books one looks. Okay, it has information on the books. So it's ISBN number, the title of the book, the author, the year of publication, and the publisher, and some image URLs, which we won't be using. We have the users data frame. It contains information on the users on the website. It has the IDs, the location, and the age of the user. And for ratings, we have a simple did user rate the book and which rating the user left. So this will be maybe more straightforward than the previous example because it's intuitive how we need to connect the nodes. And again, we need to define the nodes, the edges, node features, and labels. Here we want to predict the rating of a book, the rating the user will give to a book. Okay, so now the nodes must be separate. We need to make basically two lists for nodes because they have different features, different shapes, which can't fit into one joint feature matrix. This means also that we will need to define message passing GNN layers a bit more differently, but thankfully PyTorch Geometric has a framework and tools that deal with this very intuitively and easily, and it's very simplified to work with. And the main idea is like something like this. We have this heterodata class that will use to initialize the heterodata instance. And basically you define in this case, two types of nodes, books and users, and their separate feature matrix. And also you define different types of edges. So here we only have one type. It's user rates book. We get the edge index, and you can even define edge attributes. And I think here we will, I think, okay, no, we don't, I don't think we have, I'll see, we don't have edge attributes for this example. But you can do it. As you can see, it's fairly intuitive. Okay, for this example, we will use books. Again, we need to map the nodes starting from 0. And we will do that the same way we did before. Again, I think there are many ways for you to do this. I just picked this one. Yes, so unfortunately, our ISBN now is just an integer, but this data doesn't have many useful information for the books. Only like the authors, the titles, publication, and publisher. Ideally, you would want to have more information or somehow extract some that is meaningful. But just I think here I will only like encode some of this data. I will show you later. We also do the mapping for the users. Now they have integer IDs. And we also need to, no, don't forget to convert the ratings data frame so it follows the same principles. So yeah, now everything is as it should be. And yes, again, like I said, not many useful information is here, but for the books, we will use book author, year of publication, and publisher for features. And we also need to convert this string information into numerical information, like you would do for almost any machine learning task. There are multiple ways of doing this, but for simplicity, I just use a simple label encoder, which is not perfect because it will assign integers to unique string values rather than one hot encoding that would keep track. But again, to keep it simple, I only did this. You can do more if you want to play around. Okay, so yeah, we just encoded the numerical values for book authors and publishers. And just like before, we just need to make a feature matrix, sorry. Select the columns that we want, convert them to a tensor, and that's it. For users, we will do the same, but I will only keep for example, I can only keep the state as an information. I don't need to do the whole location, but if you want, you would. And I will use the age. Here I make a column just for the state. Also, I will do some simple label encoding on the state. And now we can see each state got its unique numerical value, but again, definitely not recommended. You would probably need some one-hot encoding at least. But you gotta do what you gotta do for the purpose of this tutorial. Yeah, again, you will need to now define the feature matrix for the user. So we define the feature matrix for the books for one node type, feature matrix for another node type. And yes, that's it. And now the edges. Here we can convert them readily to PyTorch. We don't need to use the tuple notation I used previously. So source nodes, because we have the ratings data frame that is basically giving us the edges as they are. We don't need to connect them in some different way. And we just extract the edges from the ratings data frame, put them into a tensor, and basically that's it. Again, edge labels, we would like to predict the rating, so we just extract the rating as labels. If you would like to do edge prediction, I think it gets more trickier than that, but there are a couple of tutorials and I put some in the resources below. You have to, like I said, those are the specific quirks for edge prediction. I think sometimes you need to sample edges that don't exist, so the model can predict so the model can learn, okay, these edges exist, these don't. How will the edge exist between this user and this book in the future? But here we're just predicting the ratings, so it's a bit simpler, I think. We don't sample negative edges. Oh yeah, and if you want to do this, if you want to do recommendation algorithms in graph neural networks, when they say negative edges, they mean edges that don't exist. That was a bit confusing for me at first because in network science negative edges are something different. But yeah, if you do these tutorials, negative edges are the edges that don't exist. Okay, yeah, I would like to show you like a brief, very simple visualization of this data. This is what we call a bipartite graph, which means we have two different node types, which are connected to each other, but not amongst themselves. So this is just the way you would visualize this in NetworkX. You have this bipartite layout. You defined, I defined just different colors for different nodes. So on the left side, we have users, on the right side, we have books, and we can see like for this, I use only a sample of 15 nodes. We can possibly have meaningful visualization for the whole network. So yeah, this is how it looks. Again, you can color him, you can add coloring options as you'd like. And yes, again, I forgot to mention this earlier, but when you're dealing with graphs and networks, if you have larger graphs, you will see the plotting like can take a while, especially if you have a different graph. But I would like to add, if you are not used to dealing with networks and graphs, these like visualizations of the graphs themselves, most of the time won't be useful. They look cool. They can get you like a sense of how the graph looks, but especially if you have large graphs, you won't. Most of the times you can't exactly extract some visual information from the graphs, from the visual representation of the graph. And if network science, if you want to do network analysis and graph analysis, so get into that, you will see there are a lot of different metrics that describe the graph, describe the structure, a lot of different things you can, statistics and all of that you can extract from a graph, and then you can plot that information and not the graph itself, and you will have more useful information that way. But this is just for visualization purposes. Okay, so sorry, I got carried away. Yeah, now we need to define. Okay, now we need to actually, to convert our features and to put them into a hetero data object. Again, simple. We just define create an instance of an object. We assign the feature matrices of both users and books. We create the edges. In our case, we have only one edge type. This is user rates book. Get the edge index there. Get the labels of the edges, and that's it. Just to be sure, we need that. So we need to make sure that to add here the reverse edges from books to the users in order to let GNN do message passing in both directions. So we just I think we convert the data to okay, I don't think that was maybe necessary now that I think about it. But yeah, this is already undirected, so it should be able to do it. But just in case, let's run this. I copy pasted this for a movie ratings example, but yeah, you can. I need to think about if this is necessary, but if PyTorch Geometric says it's necessary, I found it better to leave it here. And now the splits. Now you have this, again, the function PyTorch offers. You don't need to type anything yourself to split the links to train and test. And now you see we have a bit more information than we did before. Now we have the users, the books, additional information on the edges, and that's it for the preparing your data. And now the harder part is defining models that work on the your data set, in this case when there are multiple types of nodes. Thankfully, again, PyTorch Geometric can transform these models to handle heterogeneous data. And here we just use a simple model. We defined, in this case, 3 different classes that we'll use for the 2 different classes that we'll use in the final model. So we will define the GNN encoder, which will do message passing between the nodes to get their representation. So no learning here, just encode the nodes, like message pass all that information that I talked about. This is the new representation of the nodes, both the users, both the books. And you'll see this is done for the users and the books. We only need to add 1 line in the code to make this work. We don't need to type separate models. Then we define the edge decoder for predicting the edge values, which this edge decoder combines nodes representation to predict edge values. So it basically stacks the representation for the user nodes and the book nodes, stacks them together, and then does some prediction. And finally, the model combines both the encoder, this part and this part, to a complete recommendation system. So first, define the layers, which would be the GNN encoder, and this is the line that does all the thing for us. So self-encoder equals toHetero. This toHetero function converts the model here to, like, it prepares the model to handle heterogeneous data. So we didn't need to type anything specific. PyTorch already will do that for us. And then the decoder and the forward function, again, which will take these representations for the edges and do some prediction. Okay, so yes, we see the layers here. This is something I just wanted to see how the edge index dictionary looks like. Again, training and test loop. You need to, when defining in the model, when you need to do predictions, you put in dictionary for the feature matrix, the edge index, and the edge labels. And you see here we did we've put the whole X dict information and edge index both for the books and the users, and PyTorch will handle that behind the curtains for us. We don't need to do a lot. And yes, that's it. You would just do some training and get some predictions. I think that's it for me. If you can have any questions, you can ask them. I've left here some additional resources, which are, I think, very, very good, and especially if you're a beginner. So if you would like to look at some similar tutorials, if you would like to do some more ideas for more GNN projects and to get into graph machine learning, I put this. And at the end, if you would like to know something more about network science and network and graph analysis, I put a couple of links down below. So yeah, I think that's it. If there are any questions, I'm feel free to answer them. Thank you for tuning in and listening.
Thank you, Darja. It was very interesting, and thank you everyone for watching this tutorial. If you have any questions, feel free to ask them.
I see one question here from Marco. Thank you, Marco. Glad you enjoyed the presentation. How changing the Sage layer to get layer in the encoder affect the model performance? Actually, as you see, I slickly didn't run this code. I mean, it works, but I think the data, I've reduced it too much, and there's no information on not too much information in this data set. I just wanted to focus on how would you convert the data so it doesn't do, like I see, nothing happens. Still not sure why this happens, but I think it's the vectors are not, the numerical values are not good that I provided, and the data is very, very reduced. But in general, I don't, Sage, I don't know. I mean, like in machine learning, you would try GAT, try Sage, and whichever gives better results, you would use that. I think they used here Sage as Graph Sage as an example. I think Graph Sage is good. I didn't use it much, but I think it's good if you have larger graphs, because it can do some efficient sampling. And also, both GAT and Sage are inductive models. So if you would want to use this model to predict on incoming data, new data that the model hasn't seen, this would be the layers to do. But for example, GCN can't do this. So yeah, the answer to a question, sorry if I got carried away, is they work differently. They use different, they combine the information differently. One is not better than the other. You would need to try and see what works best for your case. I hope that answers your question. Katerina, thank you. Thank you, Darja. Thank you. Glad you enjoyed it. I still do not have the link for the notebook. Can the organizers send the link? So Veljko, please send the link.
Yes,
yeah.
for the link, they can check the answered question. I've put it there.
Answered questions. Yes, in the question Q&A section, you have the answered sub-tab, and you will see it there. But if you have trouble looking at it, I'm sure we can set it again. Okay, the other, there was this question, person, okay, so we answered it. To other tutorials, here they're all in the notebook. They're all in the notebook, so if you go to the notebook, you will see the links there. Again, and you Google stuff, research your own. I just think these are so you not get overwhelmed. So if you don't want to get overwhelmed, I think these are the good places to start, because I had also, when I got into graph machine learning a couple of years ago, I also had this problem, because back then there wasn't many information, and also a lot of I didn't find the information I found and the tutorials I found. It took a while to find the beginner friendly one. So I think this would be good starting points if you want to continue playing with this kind of approach. And I don't think there are any more questions. So again, feel free to ask anything. And again, thank you for joining me. I'm glad, and I hope you liked it and you find it useful. And thank you to the Data Science Conference organizers for inviting me to, for allowing me to give this tutorial.
Once again, thank you, Darja. It was a pleasure.
Thank you. So I will stop sharing now, and enjoy the rest of the conference, and see you maybe in Savat Center. And again, find me, approach me, ask me. I'm a nerd and would like to talk to you about this stuff. So yeah, have a great day and enjoy the rest of the tutorials. Thank you, guys. Bye-bye.